Bayes classifier and perceptron, and we are trying to draw an analogy between these two. Bayes classifier is a very well known classifier that solves the pattern classification problems in the most classical way, whereas perceptron is the elementary form of the neural network that we are considering. So, is there any relationship between these two? That is what we are going to discuss today. And before we begin today's topic, let me just add one or two points pertaining to the last class when we were discussing about the perceptron convergence theorem. Okay. So, I think one point which I was trying to emphasize upon is that the two alternative ways of approaching the bounds for the W0 was that we were trying to find out first a lower bound that must exist on the W0, okay, and then we tried to work out an upper bound for it, and then although both the lower bound and the upper bound will be fulfilled for the values of n which are sufficiently small, the range would be quite small. But as you have seen that with the iteration n, okay, the lower bound and the upper bound, they change, and then ultimately we have a point, okay, where we are going to have some value of n max for which the two inequations must be satisfied with the equality sign. And so that was the n max that we were looking for, and it is that n max which is, before which, within which the convergence is going to be guaranteed, and mind you, once again, that's subject to some constraints. And what are those constraints? Number one, the linear separability, which is of course a must, because only then we can use perceptron for pattern classification. Number two, W0 equal to 0 vector, okay. Number three was that eta was equal to 1, okay. Now, let us just discuss briefly that whether these assumptions really affect our result or not, okay. Especially the last two, the eta is equal to 1 and W0 is equal to 0, okay. Now, W0 is equal to 0 is something that we had assumed without any a priori idea about the patterns, that means to say no a priori idea about the weights, and it was logical to assume that W0 was equal to 0. In fact, if they are not, okay, if W0 has got some non-zero vector value, okay, any random initial value to start with, all right, then the convergence will be there, of course, okay. Of course, it is not possible for you to exactly predict that whether the convergence would be faster or the convergence would be slower, okay. If the W0s are selected, the first iteration W0, okay, if the initial weights are so chosen, okay, by sheer luck, we choose W0 such that from the initial patterns only, means from x1, x2, etc., all these patterns that we are feeding, there we have the correct classification. Means by chance if we happen to choose it at the hyperplane of the separations that we are having between the two m-dimensional spaces of C1 and C2, then of course the convergence would be slow. Then the convergence would be very fast. If it is very close to the hyperplane accidentally. Whereas if it is farther away from it, then it needs more iterations. So convergence will be there because of linear separability. A solution of W0 indeed exists, okay, and that's why the convergence will be there. Whether faster or slower will be dependent upon what type of classes have we defined in our pattern set and what is the initial vector that we choose. Regarding eta, okay, one point is very clear, that we have chosen eta equal to 1 in this assumption. Now, supposing we make eta smaller than 1, in that case obviously the convergence is going to be what? Faster, slower? Convergence is definitely going to be slower. So, we can expect an increase or decrease of n max? Increase of n max, because if the convergence is slower, then you are going to require more number of iterations. So, that means to say that n max is going to increase. Okay. Now, again, one thing is there, I think somebody was asking me at the end of the class that what is the guarantee that we reach W0? Well, I am not saying that we have to reach W0 only. Okay, W0 means the optimal weight. I mean, what I suggested was that there is a solution W0 that exists, okay, such that the hyperplane equation W0 transpose X is equal to 0. That gives a separating solution between the pattern class C1 and the pattern class C2, okay, but doesn't mean that this hyperplane is unique. Okay. There may be many hyperplanes. In fact, it is not that W0 is something that is unique. I mean, we can reach any solution, okay, that is ultimately able to separate the two pattern classes will be acceptable to us. Okay. So, there is a domain of W's, okay, which should satisfy this relationship. So, it is not that we have to reach an exact value of W0. Okay. In fact, that is not the idea. The idea is convergence, means ultimately you come to a stage when after feeding the patterns, okay, you are going to have a correct classification of the patterns. Of course, one point is there that we have analyzed it for the two pattern cases, I mean two class case, C1 and C2. Of course, this may be extended to multiple classes where we can utilize, okay, more than one perceptron. Okay, supposing you use two perceptron, one classifying between C1 and C2, the other classifying between C3 and C4. Such kind of things are possible for us to extend this whole idea of classification into more than two classes. But the elementary number of classes, of course, we are taking it to be 2. Okay. So, that was some some extra discussions that I felt that would clarify any of the doubts that you people have in your mind regarding the perceptron convergence theorem. Any doubts at this stage before we begin today's topic, that is about the Bayes classifier and perceptron. Okay. Now, primarily we are trying to draw an analogy, as I mentioned at the very beginning of the when I presented this title. Now, Bayes classifier, I don't know that how many of the participants here or the viewers watching this program at a distance, okay, are having ideas about the classical pattern recognition problem, okay, where you happen to learn the Bayes classifier as a very basic tool for that. Okay. In fact, Bayes classifier is one of the very popular classical approaches for pattern classifications. Okay. And we are going to, before we draw an analogy about perceptron, because perceptron we already know, okay, but just a brief overview of Bayes classifier I am giving in case most of the participants do not have ideas about the Bayes classifier. Okay. In case you do not have, I think some amount of overview would be necessary. And here also we are going to consider the simplest case of two pattern classifiers, that is the classes belonging to this are C1 and C2. Okay. Now, one thing is there that for the case of Bayes classifier, it is shown that when the patterns are having a Gaussian distribution, when the patterns are chosen from a Gaussian distribution, in such cases, okay, it is shown that Bayes classifier becomes a linear classifier problem. Okay. Bayes classifier in the log likelihood sense, which we are going to come later, okay, is going to be a linear classification solution, okay, exactly like the way our perceptron does. Okay. Of course, the difference is that in the case of perceptron, we are not making any a priori idea about the probability density functions of the patterns, okay, belonging to the class C1 and C2. Those distributions could be anything arbitrary. The only thing that we are stipulating for that is that the pattern classes are linearly separable. Whereas in this case, mind you, that when I am talking of the Bayes classifier, then the pattern classes that we are having, they are, I mean, since they are Gaussian distributed, and both the C1 and the C2 classes, okay, will have their patterns distributed in a Gaussian way, in the manner of a Gaussian probability density function, they should necessarily be overlapping, because theoretically two Gaussian functions we cannot have as non-overlapping case. So there lies one of the difference, okay. But let us have the basic introduction to the Bayes classifier, okay. Again, as I told you just now, that it is based on the two classifier stages. Now, here the basic thing that we are going to do for Bayes classifier is that it is based on what is called as the average risk minimization. Okay. Now, I tell you what it means. Okay. We are going to define a risk function, okay, that considers a weighted sum of correct classification and the misclassification. Of course, when we make a weighted sum like that, in that case more weights should be given to the weights pertaining to the misclassification, because when I say minimization, that means to say that we have to minimize that risk functional. So minimize that risk functional obviously means that that should have an effect in minimizing the misclassifications that we are getting out of the system, right, out of the classifier system. So definitely when we are putting up a weighted sum, okay, the idea should be is that more weights should be put to the misclassification. So just to present that simple model of the risk function that we are going to define, okay, we have to define beforehand just a few elementary quantities. First is a probability pi that we are saying, okay, which is an a priori probability that an observation x vector, in fact what the x vector that we are drawing is out of a random vector capital X. So we take a random vector capital X, okay. So this is a random variable in a vector form, and small x that we are considering is just an instance of that random vector. So small x, mind you, is an instance of the random vector x. So what we are defining by the probability pi is, it is some kind of an a priori probability whose idea you might have or you may not have the a priori idea. In fact, this probability, the initial assumption of probability is not that something which is going to matter in a great way later on. We are going to hop upon that point later. So it is an a priori probability that the observation vector x, okay, observation vector is small x, because that is an instance of capital X, is drawn from the subspace Hi. Subspace Hi, where I is equal to just 1 and 2, because we are having two classification problem. We are only having two classes. So Hi's I can be either 1 or 2. So what does Pi says? That with a probability, it just gives us a probability that it is drawn from the class Hi. That means to say that if it is drawn from H1, the probability is P1, and if it is drawn from H2, the probability is P2. In absence of any a priori idea about the probabilities, okay, lot of times what people do is that take P1 and P2 both equal to half. Okay, in fact, that's also quite a reasonable assumption, but I'm not going into the specific case of P1 and P2 both equal to half. Let's say Pi, okay, that the probability that is drawn from this subspace Hi. Now, obviously, here by the very basic nature of this definition, and because it is a two classifier problem, P1 and P2 should be P1 plus P2 should necessarily be equal to 1. Okay. So, that is one of the definitions that we are having, and the next is Cij, which is a cost function. In fact, Cij is the cost of deciding, means cost of classifying, deciding in favor of class Ci, when the actual class is Cj, okay, and here I and j both could be 1 and 2, meaning what? What is C? So, that means to say that we can have 4 such cost functions, right? C11, C12, C21 and C22. Okay. What is C11? C11 means that its actual class is 1 and the classification that we have made is also 1, which is a correct classification. What is C22? Actual class 2. The classification made by the classifier is 2. So, C22 is also a correct classification into class 2. But what does C12 and C21 indicate? They indicate misclassification. Okay. So, C12 means that it is drawn from the class C2, but we have assigned it to the class C1. Okay. And likewise, C21 will mean that it is drawn, the pattern is drawn from the class C2, but actually it will, it is classified into C1. Again, C1 it is drawn and it is classified into C2, so that's also a misclassification. So, C21 and C12, they are misclassification cost functions, whereas C11 and C22, they are correct classification cost functions. So, we should necessarily have C11 and C22 as very small quantities, right, whereas C12 and C21 would be having relatively larger values. Okay. Now, other than the a priori probability and the cost functions, okay, we are also going to define the probability density function, because just remember one thing, that supposing here this is the class Ci that we have got, okay, and we have taken just a subspace out of the class Ci, which we are calling as the Hi. Okay. Now, mind you, this subspace or the entire space Ci, whatever I consider, that has to be drawn out of an m-dimensional space. So, naturally, when I draw a space like this, imagine it is an m-dimensional space that we are considering. Now, in that m-dimensional space, all the random variable x vector that we are considering will be distributed within this m-dimensional space, right. So, there will be some form of a distribution. So, if it is having a Gaussian distribution, then what can you expect? That most of the instances of the patterns, they will be clustered more around the mean. There will be some mean vector that will be existing obviously, and the clustering will be more towards the mean. There will be more number of patterns that could be found from that mean area, and then as we go away from the mean, it will fall off in a Gaussian way. And remember that in this case, the Gaussian that I am trying to define is an m-dimensional Gaussian. So, whatever ideas we are having about one-dimensional Gaussian function, okay, that is what we are considering most of the times in our statistical analysis, or people have extended it to 2 dimensions, those people who are working with 2-dimensional problems like image processing. Okay. But in this case, again, I mean, it's a multidimensional Gaussian that we have to consider. So, associated with that multidimensional probability density function, right now we are not making any a priori assumption that it is indeed Gaussian. In fact, Bayes classifier in a general way we can consider any probability density function, but okay, I mean, what I was trying to tell you at the beginning itself is that when the probability density function happens to be Gaussian, then the Bayes classifier becomes a linear classifier. Okay. But in general, we are going to consider a probability density function which we are going to call as fx, and in fact, we are going to define the probability density function fx of x, okay, in a conditional way, that is this x, I mean fx x given ci. This means to what? That this is a conditional probability density function. So, this is a conditional PDF of the random vector x. So, this is the random vector capital X, okay, given what? Given that the instance small x is drawn from class Ci, drawn from or we say better from subspace Hi, right. Okay. So, this is the conditional PDF. So, after defining these 3 quantities, that is the probability, the cost function and the conditional probability density function, now we go over to the definition of the risk functional. Okay. So, the risk functional in fact will be a combination of how many terms? Can you guess? How many terms should be there in the risk functional? 4 terms will be there. Okay. One is involving C11, one is involving C22, they are the correct ones, and C12 and C21, which are the misclassification costs with which we have to associate. So, definitely what we have to do is that now that we have idea about the conditional probability density function, okay, we will have to ultimately define the integration of this fx with the dx vector. So, this fx again that we are defining is, mind you, in the m-dimensional space. So, it is the m-dimensional conditional PDF that we are considering. So, the risk functional R, we can say, will be defined as follows, will be equal to C11 times P1. P1 means it is the probability that the observation vector is drawn from the class H1, right. So, it is C11 P1, okay, and integral of fx x vector being drawn from the class C1. Okay, we are drawing the x vector from the class C1 and then this multiplied by dx, I mean dot with dx, okay, where dx is nothing but the elementary vector x that we are going to consider. So, this is drawn actually from the space C1, and where have we classified? We have also classified it into C1. So, because we have classified into C1, which is the subspace over which we should integrate this function, H1 or H2? Yes, majority is saying H1, but somebody said H2. Okay. So, I mean, I was worried that why did you say it's H2? It's not H2 because in this case there is no question of H2 because we are drawing it from C1, putting also into C1. Okay, a correct classification. So, this PDF that we are considering should definitely be defined under the H1. So, we will have to integrate this probability density function over H1. So, that is one, that is the first term that we are getting. The second term that we are getting, again, I mean, before writing the misclassification terms, I am writing the correct classification ones. So here we consider C22, okay, which is the cost associated with the classification with 2, okay, I mean drawing from 2 and classifying into 2. So it is likewise C22P2 integral fx x given C2 dx, okay, and in this case the integration is going to be over H2. That's correct. Okay, so about these two terms we don't have any problem, but we are also going to have two extra terms. In fact, the contribution of those terms will be more in the risk functional, because as I said that we are going to have C12 and C21's value to be higher. So what we are going to consider is that it should be C21 P1, okay. And why P1? Because we have drawn it from the class 1, okay. So that's why P1 will be associated, and we have drawn from class 1 and put into class 2, okay, misclassification. So here what should be this? Fx x given, correct, x given C2, okay, dx, okay. And where are we going to put? No, not x given C2, sorry. We are drawing it from the class 1 only. So it is x given C1. Okay, so again I was guided by wrong feedback that was coming from the audience. So it is x given C1. Okay, it's drawn from 1 and put into 2. And what is going to be the integration subspace here? Sure. So it's a divided house. Half of the people saying H1, half of the people saying H2. Well, you have to integrate over the space where you are putting into the classification. So this should be integrated over the space H2, not H1. Okay. And the other term, the fourth term that we have to consider is C12. Now I think, I mean, even if you don't understand the thing, you can write the fourth term by looking at the simple analogy of it. Because we have put C21 here, we have to put C12 here. Because we have put P1 here, we have to put P2 here. Because we have put H2 here, we have to put integration over H1 here, and x given C1 here. So there we have to give x given C2. Okay, even if we understand, I mean don't understand, we can write it down. Anyway, I mean the logic remains the same. Okay. So it is C12 P2 integration over H1 fx x given C2 dx. So these are the four terms. Now what is the total observation space that we are having? We are having two spaces, right? One is H1, the other is H2, and the total observation space that we are having is the H1 union of H2, okay, which we are going to call as the set H. Now once we define a set H, okay, as a union of H1 and H2, definitely it's possible for us to represent, let's say H2 could be represented as H minus H1, okay, H1 could be represented as H minus H2, okay, that's very clear from this definition itself. But when I consider a union set, now if I draw the instance of the x vector, and if I ask that whether the probability that it is drawn from the subspace H, that's of course should be equal to 1. And if we consider integral fx over the H space, over the entire H space, that integration is going to result in 1. I mean integral fx x dx, if we consider, that's going to be equal to 1. So accordingly what we can write down is that this risk equation that we have written down can now be modified as follows. So there is the risk equation can be just simply rewritten as C11 P1, the first term I'm writing. So I'm going to write all these four terms, and you please verify that what I'm writing is very much consistent. So it is C11 P1 integration over H1 fx x given C1 dx, okay, plus C22 P2 integration of fx x C2, okay, dx, and all that I did was that instead of H2 I am going to write simply H minus H1, okay. And likewise the next term is going to be C21 P1 integral, instead of H2 I write H minus H1 fx x given C1 dx plus C12 P2 integral H1 fx x given C2 dx. Okay. So, just I did nothing, I mean nothing extra, I only replaced this H2's by H minus H1. But having done that, okay, having defined H2 in that manner, that means to say that when I consider these terms integration over H minus H1, that could be regarded as if to say that we integrate over H, and the integrand that we are getting, we can subtract, I mean from that we can subtract the integrand that will be defined over H1. Okay. So, we can do that, and if we do that, then integral over H, of course integral over H fx dx is going to be equal to 1. So, there will be a term that comes with a minus sign which will be associated with the H1 space. Okay. So, now that we have got here H1, here also another term with H1 with a negative sign, here again H1 with a negative sign, and here H1 with a positive sign. Okay. If I combine these four terms, okay, all the integrations being defined over the space of H, okay. So, definitely we are making use, so we are going to make that simplification, and also noting very much that C11 is less than C21, because what is C21? C21 is that it is drawn from the class 1, put it into class 2, and C11 is drawn from class 1 and putting into class 1. So, it is correct classification of 1, and this is incorrect classification of 1. So, C11 is obviously less than C21, and C22 is less than C12. That is one of the restrictions that we are having, and another is that because H is the total space, so that is why integral fx x given C1 dx, whether we call x given C1 dx or whether we call x given C2, okay, there this integration is going to be equal to 1, as you very rightly said. So, by applying these, okay, what we are going to get is as follows. You see, just try to identify some of the terms very quickly. One is C11 P1, okay, C11 P1, and then it is integral of H1 that we are getting, okay, and here it is C22 P2, and then we are getting integral H minus H1. So, now obviously integral C22 P2 that you are getting as integration of H obviously means that for that term we are going to have C22 P2 as a term that comes out directly, okay, because integration within that is equal to unity, I mean integral of H when we are considering. So, there is a term which we are getting directly as C22 P2, and there is another term that we are getting which is C21 P1. So, C22 P2 and C21 P1 will be two terms which will emerge directly, and the rest of the terms and the rest of the integration will be done over what space? H1 space, okay. And if we write these separately, what we get is that the two terms that comes out without integration, or where the integration becomes trivial equal to unity, those two terms are C21 P1 plus C22 P2 as we discussed just now, and there will be an overall integration under the H1 space where we are going to have, let me write down and then you can quickly verify that I mean nothing wrong is being written. P2 into C12 minus C22 Fx x given C2, okay, minus P1 C21 minus C11 Fx x given C1, okay, dx. Okay. Now, how this term comes is pretty clear. You see here that why am I getting this P12 C2 term? The P12 no, the P2 C12 term is coming actually from here. Yeah, P2 C12. I mean, because we are considering all the integrations within H1 space, right? Integrations over H1. So, there we definitely get a C12 P2 term with a positive sign, and as a negative sign we are going to find what? C22 P2. Okay. So, if we take P2 common, it is C12 minus C22, and in both these cases, this one as well as this one, it is x given C2. So, we get this term, no objection, and then another term that we are getting is that we get C11 P1. For this H1 term we are getting C11 P1, and the other that we are getting is minus of C21 P1, and both this will be having a common thing as Fx x given C1. So, what we got is quite correct. Okay. So, now the first two terms here, okay, that we are getting, these two are fixed costs. Fixed cost in the sense that they are not dependent upon the probability density function, okay, whereas the quantity that we have written under the integrand sign, okay, I mean under the integration sign, is very much a probability density function dependent. You can see that here the Fx x given C2 and Fx x given C1, both the terms coming into picture, whereas this is a fixed cost. Okay. Now, what is our objective? Our objective is to minimize the cost. Okay. So, we have got a fixed cost component already built into it. Why it is fixed cost? Because we have decided upon some a priori probability P1 and P2, and we have also decided about some cost function. Okay. No matter how we arrive at the cost function, but C21 and C22 we have chosen. So, it is definitely fixed. Now, that means to say that our objective would be just to consider a minimization of this expression. Now, look at this one, P2 of this minus P1 of this. Okay. If this term is going to be less than 0, if this whole quantity that we have written, okay, that means to say that if P2 into C12 minus C22 Fx x given C2 is less than or equal to, let us say, P1 C21 minus C11 into Fx x given C1, if that is the case, okay, means 0 or negative, okay, I mean if you do not take the equality sign, you can say that it is the negative thing. But if that is negative, okay, then where are you going to put it into? You are definitely going to classify it into the class C1. Why? Because this integration, please note that this integration is defined over H1, and we would very much invite a negative term into it, because if this term becomes negative, then you are reducing the cost function. So, definitely if this is a thing that is contributing to the H1 space, that means to say that if this is classifying into H1, then if this negative relationship is satisfied, if this quantity is less than this quantity, then the classification, then the classifier should put it into the class C1. Yeah. So, if this is true, okay, then this should be, so all values, so we can say that all values of x vector, all values of x vector for which, okay, this quantity is less than this, those x's should be assigned. So, for all values of x for which this is true, x should be assigned to class C1. Okay, you are absolutely correct. And of course, the opposite is also going to be true. That means to say that if we happen to find that P12 C12 minus C22 means if x is drawn in such a way that P12 C12 minus C22 fx x given C2 is greater than P1 C21 minus C11 fx x given C1. If this had happened, then we would have got a positive quantity. And if we get a positive quantity into this, okay, we should not be putting into H1. Why should we? Because if we put it into H1, then it increases the risk cost. So, we should not put it into H1. Okay, we should not increase the risk that way. So, in that case, and because we have got only two choices, we can either classify it into C1 or into C2. So, if this is true, that is this greater than this, it should be, okay, then x should be assigned to C2, should be assigned to class C2. Okay. In fact, I mean, one can say that although I said that this one is assigned to class C1, even if we take this with a negative sign totally, if I say, because one thing is there that if it is having an equal to sign, okay, then it does not matter that whether you put it into the class C1 or class C2, because the integrand in this case is going to be equal to 0. So, it is not going to add up to or reduce the risk function cost. So, this is the classification criteria, okay, that is this P2 quantity less than this P1 into this quantity, put it into the class C1, or otherwise we put it into the class C2. Now, this is quite a manageable form that we have got. Okay. Now, what we are simply going to do is that we are going to just define it in a bit of other way. I mean, let us take the less than sign only, I mean, forgetting about the equality, because equality you can assign to any class, it does not matter. Whether, yes, please. If both are equal, yes. So integration will be 0. The total risk is dependent on a priori probability. Yeah, so that's correct. Cost C2 is always greater than C22. Cost C21. Yeah, cost C21 is greater than C22. Yes, yes. Risk will always increase. No. You see, there is no question of risk increase, because here I am drawing the, see, this risk is not dependent upon the drawing of the function x vector. We are picking up the function x vector. Now, the point is that because we within the integration sign we have got distribution of this x vector, so that is why it is affecting. Whereas here, whether you draw x vector from C1 or whether you draw x vector from C2, that does not matter here. The PDF is not coming into. So, that is why we are saying that it is a fixed cost. Okay. No matter whether you classify it into C1 or you classify into C2, okay, that is not going to affect cost. So, in that sense it is a fixed cost. Is it understood? So, yeah. So, now this expression, the left hand side and the right hand side, I slightly rearrange, okay, so that I can say that P2 into C12 minus C22 by P1 into C21 minus C11. Okay, you see, what I have done is that I have taken this on the left hand side and brought this into right hand side. So, I have to divide this P2 into this quantity by P1 into this quantity, so that at the other end of the less than sign, I mean on the right hand side of this inequation, we are going to have fx x given C1 by fx x given C2. This is a very interesting form. Now, here you see what is the first term. First term is again something which is fixed in the sense that we have assigned a priori probabilities P1 and P2, okay, and we have also assigned the cost function C1, 2 and this thing. So, this is definitely a fixed thing. And another thing you note that C12 minus C22, what will be the sign of this? Positive, because C22 is having a lower cost. C22 means it is drawn from 2, put into 2. C12 means it is drawn from 2 and put into 1. So, obviously C12, the cost function of misclassification is going to be higher than the cost function of correct classification. So, C12 is greater than C22 and likewise C21 is greater than C11. So, that means to say that this quantity that we are having is going to be positive or negative? Positive. Definitely positive. So, this is called as xi. So, this is defined as a quantity called xi, which is called as the threshold. And very clearly it is a threshold in the sense that if we can say that if this quantity, that is fx x given C1 by fx x given C2 is greater than xi, then what classification? Then x vector is assigned to, then x is assigned to C1. So, definitely xi indeed acts as a threshold of it. Okay. If it is less than, we are going to assign it to C2. If it is equal to, assign it to any class, does not matter. Okay. Now, this quantity is a ratio of what? PDF. Ratio of the PDF. Okay. That means to say that this PDF is what? Likelihood of C1 and this is likelihood of C2. So, this we can call as a likelihood ratio. So, this is what is called as the likelihood ratio and this is defined in terms of the likelihood of what? Likelihood of x vector. So, that is why we should write it as the likelihood ratio we are expressing as the capital lambda of x vector. Okay. So, what we are going to have, and mind you, even this also is going to be positive, correct. So, likelihood ratio is positive and this lambda x, okay, lambda x, if that is greater than the threshold xi, then x is assigned to C1, and if lambda x is less than xi, then x is assigned to C2. Equal to, you assign to anything, does not matter. Okay. Now, okay, so this is the essence of the Bayes classifier problem. Okay. And we can simply just show it, represent it in the form of a very simple block diagram. So, in that what we are going to have is that we are going to have a block, the input of, to which is the x vector, okay. And in this block we are going to calculate the likelihood ratio. So, here we are going to compute the likelihood ratio. So, we can say likelihood ratio computer. So, in this case what are you going to get out of the output of this block is nothing but this lambda x, okay. And here there is a decision box, okay, that will give the classification output. So, here the output will be either C1 or C2. So, in this case we are simply going to have what is called as a comparator. So, there will be a comparator and it will compare this lambda x with what? With xi. Okay. So, lambda x will be compared with xi and in that case we will be assigning x vector to the class C1, okay. So, it will be assigned to class C1 if lambda x is greater than xi, or otherwise it will be assigned to class C2. Now, this is the simple way of computing the likelihood ratio. All right, I mean simply looking at the ratio of the probability density function. All right, but one thing is clear, that yeah, I mean we often need to I mean compute the I mean we want to utilize the dynamic range of this likelihood ratio. So, that is why I mean rather than computing the likelihood ratio directly, it is very often convenient to take the logarithm of the likelihood ratio and then make a comparison based on the logarithm. So, what we are going to do is that we are going to compute the natural logarithm of lambda x as well as natural logarithm of xi, okay, and going to compare these two. And in such kind of cases, the likelihood ratio that we are going to compute will be referred to as the log likelihood ratio. So, I mean just putting it in a logarithmic way, we can say that your x vector is the input, and then you are going to have here a log likelihood ratio computer, and then you are going to get here log of lambda x. Log, mind you, is the natural logarithm. Okay, I mean I could write it as ln, I mean does not matter. So, here always understand that it is the natural logarithm, and here this is the comparator, okay, and here we are going to have the log of the xi function, and here will be the decision that if log of lambda x is greater than log of xi, in that case assign it to the class C1, otherwise you assign it to the class C2. So, two very interesting things that we are finding is that one is that the data processing of Bayes classifier only involves the likelihood computation, because other than that there is no other computation. So, it only involves the likelihood ratio computation, and the computation is independent of, now here the likelihood ratio that we are computing, that is independent, completely independent of whatever C1, C2, etc. we have, I mean C11, C12, C21, C22, etc. we have chosen. It is completely independent of that. All that we need is the probability density function of these two. Okay. PDF of fx given is C1 and PDF of x given C2. Okay. Other than that, we do not require those. So, computation is independent of C11, C12, C22, C21, C22, P1 and P2, all the a priori assumptions that we are making, a priori assignments that we are making. But that says only that this likelihood ratio, log likelihood ratio is not dependent upon these factors, okay, but definitely the decision is indeed dependent upon C11, C12, C21 and C22. Why? Because ultimately these parameters indeed affects xi. So, if it affects the threshold, then naturally the decision making is very much influenced by the choice of these parameters, but the computational part is only this. So, this is a great advantage of the Bayes classifier. Now, in this class actually I intended to I mean show that when the probability density function fx of x is going to be Gaussian, okay, then we could show that the classification decision that we are having, that means to say computing log of lambda x and computing log of xi, okay, and making a decision based on that, okay, the decision boundary equation that we are going to get is a linear equation that we are getting. I mean, when the probability density function is happens to be Gaussian. I mean, I intended to do that in today's lecture, but I have to shift it to the next one, because you know, I mean, always one thing happens that I mean, which at least you, the distant viewers, will not be able to see, that I am afraid of one thing when I conduct this lecture, that the person always comes to me with a sign like this, 5. So that means to say that I have got only 5 minutes, and I think the person has already alerted me 5 minutes back that my time is going to be over. So I mean, I should not be eating away into the time and pose difficulties. So we are going to postpone this discussion. That means to say the further analysis of the Bayes classifier in a I mean, assuming the Gaussian probability density function, okay, showing it to be linear, in the coming class. Thank you very much.